All right. I hope you can hear me and see me now.
Yes, we can.
Yes, we can.
Fantastic. Well, I'm not so sure it's an improvement, but at least the camera is working and we can, we can, yes, of course, it was an update that was coming. So that postponed us a couple of minutes. We'll try to catch up. I hope everything was okay with the previous lecture. Let's have a quick recap. Can you see my presentation now?
Yes.
Very good. I recorded last session, and I'm hoping that you will allow me to record this session too for your convenience, so that you can look at it later as you see fit.
Okie dokie.
Very good, thank you. Right now, this is the overview of the topic, advanced casing design. And as said, you guys are free to comment what you want to repeat more, what you want to add, or if there's anything, anything at all you would like to comment on. So this is basically based on last year's overview. We covered basic material science in the previous lecture. We're going to do a quick recap of that. We talked about the atomic level lattice structure of steel metals and how the different processes in manufacturing of pipe actually influences the steel and its properties, and how it's connecting back to the atomic level and how it works, and of course how we reintroduce properties that are turned in a way sour for us during this process of manufacturing. One thing that is essential for us would be the yield point of steel. We see the stress strain curve to the right. We talked about that part, and we said that point A on the stress curve is the yield point where you have 0.2% permanent deformation, and that's very often the design limit in casing design, the yield point. Why? Because we don't want our pipes to deform so that we lose drift through them. Yeah, we'll talk more about how overextending our limits will make things difficult for us when it comes to working with casing, tubing, liner. We also remember that what is in the colored part to the left would be seamless pipe, meaning that there's a physical rod coming out of the steel melt, and that it is pierced. You can see it's a kind of small here, but it's pierced with a spear, and then it becomes hollow, and then it is worked over and over again until it has the right properties. And through this process, it is reheated and it's cooled off in order to keep the right properties of the pipe. To the left in black and white, we have the welded type of pipe, which would be typically from size 20 inch and above. You will of course get special sizes like 13, 5/8 and so on, also in welded qualities. meaning that you'll probably get whatever you like to order with the casing tubing manufacturers. We talked about seamless pipes being the most typical ones in the industry, whereas for the larger size, that's where we use the welded type. And also for pipelines, we have what is called line pipe. They are welded like this, plus they are welded together drum after drum when you lay down the pipe. We talked about the, steel and how it goes from a melt until a physical form, and how grains change even in the physical state when steel has been changing through its phase diagram. Now, also what is taking place is actually at room temperature changes. Only they are extremely slow compared to when you heat it up. And everything is according to the phase diagram, as we can see here. Heating it up until, say, 400 plus degrees, changes are quite rapid. And you can say that, for example, a piece of casing normally would need an hour, and then it's fully recrystallized into whatever size that we want. We talked about recrystallization when it comes to welding is very important. And with that, I think we have recaptured last lecture, the latest lecture. Would you like to ask any questions about the previous lecture, please, or for that matter, any thing that I'm lecturing? Please just let me know, and I will address your question. We are going over to looking at the forces that act on steel. And how they are. What we are used to from our teachings and studies is that anything is working and acting like a vector. That is not entirely true when it comes to loading a piece of steel. We are now looking at something called St. Venant's principle. And to the right, you can see the same specimen 3 times, analyzed for stress through a notch, through a hole in it. And you can see that it has been loaded differently. At the bottom, it's like a point. At the top, it's an equal loading, and in the center, it is an uneven loading. And you see around the notch, it has the exact same stress, regardless of the point loading. This is how steel actually works. And for that, what we do is addressing what St. Venant found out. It will act basically like a distributing effect if it's a certain distance. When the distance is large in comparison with the linear dimension of the surface on which the forces are acting or changing. That's the principle of St. Venant. Knowing this is quite important, and the effect of it is this. We are decomposing the acting stress. We are decomposing it, and we are decomposing it into 9 components. You see them all in this unit cube, X, Y, Z. We have shear stresses along these surfaces, all of them. The front face, the right face, the back face, and the left back face, and the bottom and the top. and that becomes in a 9 vector matrix. When we set this up in what we call the principal stresses, it becomes this equation we see in the bottom here. We call this system for a tensor, a stress tensor. That is what is going on in steel. We have a stress tensor, not a vector. 9 components. What is good for us in casing and tubing design is that when, well, it's actually the same as in any other science, of course, that when you use principal stresses, all these shear forces, they go away, they turn to 0. So you only remain with the principal stresses. I hope that you guys have had the course rock mechanics at NTNU. That's at least where I were introduced to principal stresses and studied them. We have a simplification, you may say, in casing and tubing design. We'll quickly look at it. The principal stresses are here as they are working on pipes. In this situation, it is inner pressure larger than the outer pressure. And we'll see that the radial force, sigma r, is positive. And the blue arrows, sigma theta, or the hoop or tangential stress, that's always the larger stress, more or less, in any case. I'd say in 99% of the cases, the sigma theta is the larger, sigma radius would be the smaller, and the axial stress, which would be a decomposition of the weight acting, corrected for buoyancy, for example. Yeah. We'll look into those details later on. But these are the 3 principal stresses. I am in a meeting, honey. I need to be here. You have to talk to Kutsi. All right, and here with the, sorry about the disturbance. Here are the expressions for the principal stresses for pipe. We can thank Mr. Lamé for these principal stresses, and that simplifies everything so much. We can now design or find the limit. We can find the limit. We input whatever is the acting forces in any situation, and we see it up to the limit of the yield. So that simplifies things quite a lot for us. You can see that what goes into these expressions simply is the radius of the pipe. It's the inner and outer pressures. And of course, for the axial stress, we need to calculate the acting weight. It's like I said, decomposition of the weight, corrected for any other factors. Yeah, temperature would typically be one of the most important factors actually in the axial stress. We will get back to all of those things. Don't worry. These are just to give you an idea about what it all comes down to. It all comes down to the 3 acting principal stresses. That's where we are. And that's also in this small call it exercise where we, from the last time we saw that this is a load cell where you are doing only axial stress. There will be no tangential or radial stress here, only axial. It means that all the principal stresses go to zero except for the vertical. So the expression becomes like this. Historically, this equation has been very important. It came about, if I remember correctly, in 1913 officially. There are some stories around that there was somebody else talking about it earlier, but through all of history, this is what sits with the German von Mises, and it's also called the maximum distortion criterion. And we'll later on see how that expression actually goes into an ellipsis, which was first drawn by somebody called Heinrich Henke. Excuse me. When we saw the linear part of the stress-strain curve, we talked about Hooke's law, and that one came about before 1700. Euler talked about Coulomb theory, meaning what we'll see later on is that if a piece of pipe has external pressure, and now in that context, very often what people can relate to is the experiment of standing on a soda can. You can stand on a soda can, and if you just touch the side of it, it completely flattens. With just a tiny impact to the side, it collapses, and that's called buckling. We talk about collapse, but in many cases, pipe and columns, they collapse, and this was first expressed by Euler. Then the one that gave us the stress tensor and how actually stresses works in inside of metals and solids, homogeneous solids, that would be Cauchy, and that's the stress tensor that we just saw. Later on, we're going to see how internal pressure is governed by Peter Barlow's law. That is still used today. It's from 1836 and way long before modern science in this area was developed. So it has to be used. What the industry is using is his law, the law presented by Peter Barlow. It is close to correct, but some of the presumptions are not entirely correct, to put it mildly. And these are Otto Moore with more circles, one of the first failure theories to be presented. And then Lamé, we saw his theory of simplifications for tubulars, where we can have the principal stresses. St. Venon, he showed how things work. Then we have the Tresca. I am in the meeting, honey. The beauty of having home office. And then it's von Mises, like what we saw just now, the failure criterion related to yield. Sorry, little one. No, go to Kutsi, please. And then Heinrich Henke, like said, that maximum distortion energy, or von Mises equation, it turns into an ellipsis that we can see. The last one there is beyond what we are going to lecture in this in this class. We're now going to look into well construction a little bit, and the principles of it, to just give you the fundamentals of so it's easy to so it's easy to relate to the casing design. There are so many aspects of the topic. Remember what I said the last time, we are designing for the life cycle. We have to presume and look into all of the different aspects. And here is the overview of the topic of what we're going to look at: the introduction, casing setting depths, and the number of casings. And we're going to go very quickly through this topic, not touch too much on it. The naming is quite clear. We'll look into the specifics and what is important for each one going on here. It's the conductor. That one is actually very, very essential and has some very, very special features. The surface casing and what it means, intermediate casing, drilling liner. That's one that does not take part of the integrity, but would be important in order to reach our goal. A well that is producing from the target set. Production casing liner has very, very important aspects. And then, of course, we have tiebacks. The essential components in casing and tubing design would be the Christmas tree itself. We have the wellhead. We can see that in light blue here. And then what we can see is what we call a starter head. For land-based well construction, we also very often have what is called a cellar pipe. What we'll do here today is talk about both land-based wells and offshore wells. And we will talk about the differences, but to say that right away, the similarities are very strong. Here we see how well construction is started. Typically for land wells, this gives you a quick overview. What we do is to excavate the ground, and we make, let me just show this slide very quickly. You excavate the whole area and you make cement. You have a certain area that extends for the length of the beams of the rig. There will be steel beams on top of this area here where the rig is resting. So the rig comes up here, and typically from this point and up, it's typically 10 meters up to the rotary drill floor, rotary table. And in the construction of making the well pad for an onshore well, you install a small pipe that you just cement in, and you kind of reinforce around it a little bit. Yeah. What is important at this point in time is that the ground is solid enough for you to start drilling without washing out the whole area, destabilizing the concrete. Remember, concrete is very strong in compression, but in tension it doesn't take so much force. So call it the construction failure of having too soft ground will destabilize the area, and the whole rig will start to lean over. Now, this is what it looks like. This would be the cellar pipe, and there are some beams here to support weight, and later on it will be chopped. Like you see here, this would be in light blue the beams, and the conductor is set and welded together with this later on. The reason why you have a cellar like this is to take returns while you are drilling for the conductor, and sometimes also for the next section. So you have like a suction going down, taking out the mud returns. Once the well is finalized, we see an old style Christmas tree here, and typically it's just a Christmas tree coming up, and the wellhead part is sitting down in the cellar. Comparing the subsea system with the onshore system. To the left is of course the subsea 3. In purple we have what is similar to the starter head of the land-based system, and inside it sits the wellhead itself with all the other casing hangers. This wellhead sits on the 20-inch casing, which refers to the surface casing, and is very often drilled without any BOP. It's the same here. You have the 20-inch casing very often sitting on the wellhead. Now I see in this drawing they have made that to the conductor. It varies a little bit depending on your well construction. Principle would be the same. Yes. Let's see. I don't think we will go into much more details. What we will see later on is a video that shows how the different casing hangers that sits inside here, how they are installed and how it works. And we can see some pictures of it. We just saw how it works starting construction onshore, and here is how it starts when we do the same subsea. There is a structure set in the sea bottom, and we start drilling through one of these, call it guides. It's called a permanent guide base. Just a second. So we see down in this corner, we see to the right, we see how the permanent guide base is sitting with a 20-inch as it is lowered down into the guide of the manifold or subsea structure. Yeah, I think what we will do, we will start the video after the break, where we see all the casings and how they are connecting together. That will create a much more coherent presentation. What we can do, we can proceed for the next the remainder of this part of the lecture with an overview here of the different casings and how they are how their importance, to put it like this. The conductor would of course be installed to stabilize the foundation for the infrastructure. Onshore it would be the rig. Like said, if it washes out under the well pad, typically the rig would destabilize. Yeah. And the conductor has a very, very important role. It holds down the entire well. We will look more into it, but unless the conductor is properly cemented in place firmly to the formation, we risk that the whole well will actually expand up because it's often heated up for wells that are producing oil and gas. Increasing the temperature will elongate the metal in the casings and the tubing, and the whole well will start to rise up. And what we're talking about here is, for example, for offshore, if you look at the template, we see that there is one center pile here, and the conductors in each corner here would typically stabilize the template from also tilting, just the same as the rig. So it's the conductors have a very important role, as per se. And we'll talk a little bit more about each section and what are the essentials for it. First section. What we'll find for a conductor is that there is very little guidance. If you again look at this picture, you see a huge loophole, and we can imagine that this piece of drill pipe goes through the sea, normally 100 meters to 300 feet or more up to the rig, sometimes a lot longer, and a piece of drill pipe, meaning less than 7 inches, it would be vibrating a lot. You can imagine just hitting this hole using an ROV for visualization and guiding. It is quite an accomplishment. And then drilling, keeping the pipe inside this hole without vibrating too much, both the pipe and the top drive and everything else. That's quite hard. Typically having this section is a very low weight on bit compared to the surface area. It's a very large size hole we're drilling, and we cannot put down too much weight. Typically it will increase the vibrations, and typically also it is not possible. For example, for a land-based construction, what it is it's 10 meters from the rotary until you start drilling. So you have one joint. Or if you have a stand, of course, it doesn't really matter. It's you just don't have any weight available. Yeah. When you drill a conductor, it is often in the range of 50 to 150 meters long. It all depends on the stability of the formation you're drilling. As said, an important section, it has to be cemented to surface in order to hold down any thermal expansion and restrain the whole well from expanding. And what is important is an inclination less than 1 degree. For us, having less than 1 degree is so important, basically because you are going to put on a Christmas tree and you hook up this production line, a physical line that goes into the Christmas tree. If it's leaning over, you just can't connect it. And it goes for the same here on land-based wells. If it's leaning over, you will have side forces, and you will find it difficult to hook up the flow lines. You have a certain tolerance when it comes to height and orientation, but it's very important that it's less than 1 degree leaning over. And when we are drilling these sections, typically subsea, what we encounter would be something called boulders. At least in the Norwegian sector, that is very often happening. Boulders would be rocks that icebergs have been freighting, and they are embedded in the formations. So you're drilling quite soft formation compared to a physical volcanic rock. What takes place is that you're drilling and you're hitting this, call it fist size or larger rocks, and it becomes like a huge shock to the bit. And one thing is the impact into the drill string. And another would be that it kind of deviates because you're hitting a physical restraint in your path of drilling. Yeah. So that would make a deviation, and your well path becomes on the side of this boulder that with time will fall into the well, and you will pump it out or push it to the side deeper down. Yeah. So that's what takes place, and some of the main issues for the conductor section. Surface casing, we drill without BOP, which means that there's returns to sea. Of course, water-based mud in those cases. If it's onshore, you have a huge hole volume, and you have lots of cuttings to handle. Very often still you have low weight on bit because of the same reasons as before. Little guidance of the pipe, lots of vibrations. You're better off when it comes to your drill string. You can put some heavy weights and drill collars and so on to kind of reduce the vibrations a little bit. But still, it's a low weight on bit compared to the surface area. Yeah. Typically, what we're facing onshore, offshore, when we're drilling with water-based muds in these formations, will be that the shales are reacting. Shales are reacting to the water. You can try to do some inhibition with chemicals. The problem is typically, especially onshore, is that most of the aquifers of drinking water, you're drilling through them in these depths, and you're restricted with regards to the type of chemicals that you can use to avoid contaminating shallow water aquifers. The result is bitballing, meaning that the shale will stick to the BHA, and it will become like a gigantic Q-tip, and drilling is absolutely not effective at all. So very often it's low ROP for the reasons mentioned. And of course, when you're just making mud and pumping it down into the well, and you're taking returns to sea, it's very difficult to maintain mud properties. Again, you're cementing to surface. If for some reason the conductor should start to weaken its bond to the formation, the surface casing will act like a backup. For land-based wells, here is or the case where we are showing. This is where you are landing the starter head. It splits in this case differently than the subsea, but it remains the same construction. Subsea, we call it a permanent dive base, whereas onshore, in this case, we call it a starter head. Yeah, the intermediate casing, Again, the same issues if you're using water-based mud, reactive shales, so on and so forth. Now we are so deep in most cases that drilling becomes stable. We have installed a BOP, and we have much more guidance. Drilling becomes more like what we are familiar with. A nice BHA returns to surface. We can use oil-based mud. In that case, it's a very large hole and a lot of cuttings that we are dealing with. So it becomes a very, call it, busy section. This section is very important for wells that have that has a gas lift as a feature. You may have to certify the intermediate casing as the same as the production casing, because you have a connection between the tubing and the production casing where you're injecting gas. Yeah, it's a part of the well integrity. It's just something to think about. Sometimes that impacts our casing design. And formations that are cased off, they are sometimes even more reactive than further up. Could be some smectite and other really nasty shales. If we have a look at the pore pressure prognosis here, it could be important to seal off some high pressure formations. When it comes to cementing, because we are talking about a long section with a lot of volume in the annulus, it is often not cemented up to or into the next casing. One of the reasons why it is not cemented into the next casing would be controlling the pressures in the annulus. We'll look into that more once we do the detailed casing designs for each casing. It has to do with what we called in the last lecture, analysis of specific situations through the life cycle of the well. We call them load cases. What we do, I'm just going to finalize that part. When it comes to cementing, if we look again at the pore pressure prognosis, I would cement as far up so that I have a little bit of leverage when it comes to this pore pressure, so that we have this pressure covered by cement as far as I can. As much pressure as possible. Why? Because a high pressure often means that there could be seeping gas from a shale given enough time. So that's a good practice, not a rule, but a good practice for cementing and supporting the casing. And with that, we are 2 minutes over. I hope that's okay with you guys. I'm sorry, but my laptop had an update pending, which made our start delayed a few minutes. I hope we catch that up. And you guys, sorry for the interruptions. I'm having home office today, so the helpers are running in the background, and I hope that doesn't disturb you. Thank you for your attention. Any questions, please just ask. Thanks. All right. I might be slightly early, but better start and try to finish off today's topic, since we had some difficulties in the beginning of previous session. I hope you can see this picture. It's called a hole opener. Can you guys see this picture?
Yes.
Very good. this is what you start drilling with. Typically subsea and sometimes also these are used onshore, looking exactly like this. I'll just make a note of the name in black going down there, boulder buster. As I talked about, boulders are rocks carried and inserted into shallow formations, which disturb the drilling quite significantly. Now, there are more pictures to look at so that you get an idea how it looks. This is the hole opener part. In the bottom, very often it will be a 17.5-inch bit. And then comes these hole opener parts, and it goes up to 30 or 36 inches. We'll see one more picture of it so that we have a full understanding of what we are talking about. This is the size of it, and this is what you are putting down to the ground or into the sea bottom. And you can imagine trying to rotate this with either 10 meter or 200-300 meters, a minimum 100 meters of unsupported pipe. Yeah, we'll see more later on about this. Let me see now. We'll go to this one again. We'll quickly finish here what would be the important parts. The intermediate casing, we discovered it. Production casing. Production casing is the backup in well integrity for the production casing, and it has to be certified with the same pressures and stress levels as what you do for tubing. Tubing being the most exposed string that you design in the well, exposed to the highest temperature changes, which again gives the highest stress levels. The only difference in a way between the tubing and the production casing will be the corrosion resistance. So you select a different material for the string that is supposed to be exposed to flowing reservoir fluids. Often the first section with oil-based mud in many cases, that used to be the truth. I don't think that's so true anymore. Often drill down to the top of the reservoir. That's very, very important. That's a drilling design technique. So we won't cover it too much at this point. We will get back to it, why this section stops on top of the reservoir. Yeah, you always need to have a second survey so that you know that your position is accurate before you drill into the reservoir. That's one reason for stopping there. There are other reasons at least as important. And again, point number 4, as we talked about, if the tubing starts leaking, this casing will see all the loads that the tubing would have. Yeah, and the production casing sits inside or on the wellhead itself for this specific onshore well that we have been presenting here. It would be other setups or configurations, if you like, in other cases. When it comes to cementing and how it works, we see here how Yeah, here you get it. It's a 13 3/8 inch casing sitting inside. So already this is a different setup than the previous. So there are two plugs sitting inside the casing running tool, and you drop darts. You drop the first dart, and the bottom one shears out, and cement follows. And then once the cement is finished, you drop another dart and you pump mud behind it. The dart behind the cement lands in this plug here, and viper plugs, maybe they're called. I can't remember from the top of my head. And then this one goes all the way down to the shoe track, lands out, and squeezes all the cement through here, because it has like a shear disc. We're not going to talk too much about cementing. I guess you have been covered that with Besad, so we'll not cover more unless you guys want to discuss cementing more into detail. It's basically the same for a liner. A liner just has a longer, call it, way for the darts to go. Yeah, and if you're cementing a liner, you typically cement all the way back. What we're seeing on the left here in blue, this is the drilling liner. A drilling liner is to cover a trouble zone, but it doesn't really take part of the integrity configuration of the well. Yeah, the tubing design process, we will discuss that next session. What we will look into in the next session is how to find and determine the section design pressure and what it means. We will look at the acting forces. We will analyze the different scenarios that are kind of thought of as peak in any way, shape, or form. Either the low cases, low support, or high extreme loads. The development of changes given through the nature of producing or depleting, injecting, so on and so forth. We need to analyze all those cases because it's a life cycle analysis that we're doing. Our analysis will make sure that the casing holds and delivers the integrity throughout the whole life of the well until permanent abandonment. Yeah, we look at the strength of tubulars. One thing is to analyze all the forces that act on the tubulars, but we also need to understand what kind of limits, design limits do we have for the tubulars. Collapse loads, that would be external pressure. Burst, that's internal pressure. Axial loads, those are the sigma z, or decomposition of the weight or temperature stresses. Yes. Listed here, triaxial, it means a combination of the ones above. For simplicity, we isolate the calculations of the ones above, and then in real life, that's not how it works. Of course, it is a combination of all these things. Yes, we have a question. Go ahead, please.
I just want to ask a question regarding the casing setting depth.
Yes.
Like, I just want to know, like, the factors that determine the casing depth. I know few factors determine, but I just want to know the main factors that really determine, like, apart from the formation pressure, like geological factors or whatever, or the mud weight window. What?
I will answer you, and I will tell you right away that we will we will get back to this later on too in more detail, but I will give you an answer now. Let's go back to our drawing here where we see the whole stability plot. Okay. So we see different casing setting depths marked from these blue lines. And there are two things that we talk about. We talk about a casing design and a drilling design. You may say that the internal pressures are limited to what the casing can withstand, but what we do is to say that the casing has to be stronger than the strength of the formation outside. So let's say that you fill the whole entire casing here, the production casing, with gas. What will be call it the next development is not a failure in the casing, but the formation will fracture at the shoe. So that's one thing we need to determine, that the casing can hold any pressures that can go on from the sections below or open from drilling. It will be the pressure, the integrity of the formation that fails, not the casing. So that's one factor. And we call that a load case. That is a specific load case that we will be looking at. Now, there's another way of looking at it also, and that is from the drilling design perspective. The casing can withstand a lot, but it doesn't mean that it's okay to just extend it. Why? Because if you're drilling and you're ending up in a scenario where, for example, this pore pressure gets into this formation strength, it may seem simple that yes, you can't have a drilling window. The mud is not okay with that, but the problem is kick tolerance. So this is very obvious with regards to the strength in the red line and the mud, but it's called kick tolerance, and the regulations are internationally set that all sections should be able to take 4 cubic meters of reservoir fluid into the wellbore while drilling and still be able to maintain integrity. That is not a load that the casing in many cases would be the limit to. It is the type of open hole properties, the formations exposed in the open hole. Their property is what governs the kick tolerance. And the result is I have to adjust my casing setting depth so that the drilling design becomes acceptable. There is one exemption to the 4 cubic meter minimum rule, and that is sections around 12.25 inch, which in many cases would be sections that go down towards the reservoir. In this case, the requirement is even more strict. It is said that you need to have the double, meaning 8 cubic meters. You have to be able to handle as much as 8 cubic meter of the highest pore pressure. And what we do in these, call it kick tolerance calculations, is to use gas. We use gas in our calculations because it's the most extreme. Methane properties, that's what we're calculating with. I'm not going to go more into detail right now. What you said was that it's obvious that you can see that you can't really have the drilling window from the mud properties, but you have to do more calculations in order to know that the kick tolerance is okay. And again, it influences your casing setting depth. Not very visible, but absolutely one of the hard lines in casing design. Even though really the casing is not really directly influenced, it's the open hole below, but the casing has to be part of the solution for it. Yeah. Did that answer your question for now?
Thank you.
Yeah, very good. All right. We will do the design analysis, and we will do a peek into regulations, typically how governing documentation would look like. Generic ones, they would pertain to any operator, to be honest. Here is a list of the acting forces. We will not go through much into these right now. We will rather take a more deep dive into it next lecture. And again, what is at the end of this lecture would be a link to where you can find the recordings. Not so sure that the quality of this recording is going to be as good as the previous one, because I did have this update going, so I couldn't check the levels of sound and whatnot. So, but that being said, what we're going to do now, we are going to look at an animation of how casings are set. Let me see. Here. Can you now see? Can you now see this presentation here? Oh, I need to do it a little bit different. Share and include sound, of course. There we go, and here we go, like this.
Yes, we can see.
The Host 1000 system, or hinge-over subsea template system, is being used in the development of the Terra Nova field.
Can you hear the sound from this presentation, please?
Yes.
Ah, very good.
Allows for installation of the template manifold assembly through the moon pool of a standard drilling vessel. Each host system provides for the integration of up to 5 subsea wells to be drilled directly on the template and provides the foundation structure for the subsea manifold, hinge-over guide-based structures, hogs, and pig loop modules, PLM. The host systems are contained in a series of 4 glory holes that were excavated in 1999. These glory holes enable the subsea equipment to be placed below the seabed for protection from iceberg scouring.
Okay, so this is an old presentation. It is from a field that was developed up on the east coast of Canada, where icebergs are coming by ever so often. So what they did was to excavate the ground in a manner like very often what you do onshore. So the whole well is deeper than the general ground level. What takes place is that if an iceberg now comes, it passes over the well.
Once the drilling vessel is in position, the
Yeah, so here it drills a hole, and
the host center section is
this
attached to the last section of the pipe.
manifold
A
is
cam-actuated
placed
running
down.
tool is installed, and the entire assembly is lowered to the ocean floor, where the 36-inch pipe is run into the pre-drilled hole. Note, the flexibility of the host system allows for the hinge-over guide structure, hogs, to be installed independently, providing flexibility in operations. For the purposes of this presentation, they are shown run with the template center section. The host 36-inch center pile and casing are now cemented into position. Cement is pumped down the drill string and 36-inch casing until returns are seen at the sea floor. Once cementing operations are complete, the cement is allowed to cure for at least 12 hours. The host is re-inspected by the ROV to assure that it is level and free of cement. Once the host is at the prescribed elevation, the hogs are lowered. This operation is performed by the ROV, disconnecting the retaining wires on the hogs and allowing them to be lowered to the horizontal position. The ROV completes this task for each of the 4 hogs on the template assembly. These hogs will later provide guidance for the well drilling operations and the guidance equipment. The pig loop porch or PLP structure is lowered to the seafloor on a sling-type running tool. It is positioned over the host and lowered into the hinge receptacle by a downline.
Nei, du hørte hva jeg sa, vær stille, så tar
The
jeg...
PLP is then lowered to the horizontal position by
Jeg
the
holder på et
downline
møte,
and
David.
is inspected by the ROV. The ROV releases the shackle on the PLP and the installation sling is retrieved to the surface. The 36-inch running tool is then released from the center pile by rotating the drill string 3.5 turns to the right, which allows the cam-actuated dogs to retract from the center pile. The 36-inch running tool is retrieved to the surface by a straight upward pull of the drill string. Once the PLP is installed, the host must be checked for level before the manifold assembly and drilling guide bases are installed. An inclinometer is lowered on a guide wire and landed on the host in a predetermined area to measure the exact level of the assembly.
Yeah, what you'll see is that there are some orange, call it screws here, where you can adjust the inclination of the template. Now, these templates, they are installed by boats long before the rig arrives. Once production drilling is taking place. What you'll see is that if you're doing an exploration well, you may have single slot types of wells. They would have the same mechanisms as these things, but not the production part of it that you'll see later on.
At any point in the host if the host requires, the inclinometer is then retrieved to the surface. The individual well slots are drilled by installing a bit guide into the hinge over guide base and then drilling out for the 30-inch casing through the hog.
Yeah, it seems very simple here now, but you guys have seen how they look, this hole opener. I call them beasts, more or less. And to put them through these loopholes with the guidance of an ROV is quite an accomplishment in itself. Here it's very simplified and it looks like it's just a single bit in the tip there, but drilling a 36-inch hole is not done by one single bit like this.
Depth is reached, the drill bit is removed, and casing is run. The permanent guide base, or PGB, and 30-inch wellhead assembly are made up to the last piece of casing on the surface.
Yeah, we'll have a look at how this is done, because it's quite special on a subsea well. Let's have a look at the photos. So this is the whole template as per se. You see a person down here in comparison to the size of it. Let me see. So we will look at the pictures here very quickly. This is just the raw template, and this is the guide. We don't get too much information from just looking at them as per se. These are just guideposts, those white piles that you see where you are kind of guiding things on them. Let's see. There is one interesting part here. This is the equivalent to the starter head. This is where the conductor head, if you like, permanent guide base is locked until this this part here, what we just saw in the video. Here, the starter head equivalent is locked into the permanent guide base. Yeah. You see a person working with it with a safety harness, because right now they are in the moon pool of a rig. We'll see how that works, and that's the main point of showing you these photos. This is the running tool that locks into it. This is how you run it into the sea. What you see here is the moon pool of the rig, and you'll see that they're using what is called the BOP trolley. So the BOP on a subsea rig, it is on the side, and it goes on like a rails, like a train. The huge trolley, and the BOP is lifted by drill pipe or marine riser from the top drive and onto the trolley like this, that you put under the drill floor. You relieve the weight by setting the BOP or whatever it is on top of this trolley. You take off the running tool and you can take it on these rails out to the side. Now what we are doing, we're using it for the permanent guide base. The BOP is parked on another trolley on the side. You see it clearly here. Here is the PGB. You run it to the center, and from drill floor, you're lowering the casing through this hole here, all until you see the starter head that locks into this profile. Here, you see it, the trolley has come under the drill floor, and the casing is run from the drill floor and through it, like this, and into the sea. Here, the casing starter head has landed. You have the running tool inside, and you have lifted it off with the drill pipe and connected to the top drive. You take away the trolley, and you're ready to run the whole thing into the sea. I hope that was clear. You now continue, and you see it's been run on drill pipe all the way until it lands on this loop. Yeah.
Inch cam actuated running tool is made up into the 30-inch wellhead assembly. The PGB, complete with umbilical termination head or UTH port, is attached to the 30-inch wellhead and is lowered with the casing via drill pipe to the ocean floor. The guide base is landed on the hog, and alignment is provided by guides on the permanent guide base respective to the hog. The UTH ports will be utilized later for installation of the hydraulic and electrical umbilical. Further detail of the subsea drilling operations is provided in the UWD-15 wellhead section of this presentation. The 30-inch cam actuated tool is released by rotating the drill pipe approximately 3.5 turns to the right and picking straight up. The 18 3/4-inch UWD-15 high-pressure wellhead housing is made up onto the 20 by 16 or 13 3/8-inch casing strings at the surface. The assembly is lowered to the sea floor by an 18 3/4-inch cam actuated running tool that is attached to the drill pipe.
Yeah, just to mention it quickly, how this wellhead locks into the starter head is extremely important because of all the forces that are acting up. So the conductor was cemented here and into the permanent guide base, and then the wellhead sits inside. So they have to lock together, and it has to be an extreme high quality lock, taking a lot of force there. Part of the tubing design and advanced designs would be to know the exact forces that the well will be coming up with, upward forces.
30-inch casing, and the wellhead assembly is landed in the 30-inch wellhead. Further detail about the UWD-15 wellhead configurations can be viewed in the drawing section of this presentation. Once cementing operations are completed, the wellhead assembly installation tool is retrieved to surface by rotating the drill pipe and picking straight up. The host system provides significant economic and operational advantages to the operator by allowing the permanent guide bases and wellhead assemblies to be batch set. Each of the assemblies is installed and the remaining drilling operations for these wells is performed. Upon completion of drilling operations, the manifold assembly is prepared for installation. The remote guideposts are installed via guidelines with the ROV providing guidance.
Yeah. So what you do, of course, is to cement several wells at the same time. So and balance it out so that you don't finish one well on one corner. You do batch drilling on the top in order to make sure that it's level and stabilize the whole template. Now, what they're showing here is that you're running down the manifold later on, but in most cases, the template is complete when the drilling rig comes, and you do batch drilling of conductors.
Manifold is made up of a 10-inch production and 6-inch gas lift, which contains 6 by 2-inch branch lines rated at 4,200 psi working pressure. The manifold assembly is lowered into position. Once landed, the manifold assembly is inspected by the ROV to assure proper positioning and alignment. The ROV releases the installation slings in preparation for the installation of the pig loop module. The pig loop guideposts are installed from the rig floor via guide wires. The pig loop module is made up at the surface and run on drill pipe and installation slings. The pig loop allows for round-trip pigging of the manifold assembly and flow lines to maintain an unrestricted flow path.
Yeah, what we're seeing on the manifold is kind of interesting in a way, and we'll see the connector part later on. That is important for the again, it ties into the inclination of the conductor, like said. If you're more than 1 degree off, it means, for one thing, extreme casing wear because of the side forces that would be high up in the well. That's where you have the most tension and side forces, even at the low inclination. The other thing is that more than a degree is the limit, because you cannot connect to the production connector. If you see my point, you will actually see it physically here on this animation after. Now, what you'll see is that this is the production line. It goes like this, and through this pig loop, what they call it, and out here. So all the wells are in the same, producing towards the same manifold. To keep the pipes clean of wax and any deposits, they pump a pig through here to clean the pipes. So without a pig loop, you have a dead end on both sides. That's not a very good construction.
Self-contained unit can be retrieved and placed on another manifold or modified with additional. Once landed, the pig loop is hydraulically moved into position either by the ROV or a downline attached to a hot stab port on the pig loop module ROV panel. Hydraulic pressure is applied, and the entire pig loop moves forward to its proper engagement position. The ROV applies hydraulic pressure via the ROV panel on the pig loop to operate the stroking connectors. A series of ROV-operated ball valves on the ROV panel allow for proper functioning of the connectors.
Yeah, this is the connector, and it works the same on the Christmas tree, connecting to this to the manifold ends. It has the same type of connector. All of them are more or less the same. And if it's more than 1 degree inclination, it doesn't mate up, and the whole well is very nice, but it cannot produce.
The connectors are then hydraulically locked to the manifold hubs. The Terra Nova project features 5 by 2 inch, 6,650 psi horizontal subsea trees. The tree is installed using drill pipe and a standard installation tool. An associated workover umbilical termination head is also run with the subsea tree during its installation.
Yeah, so this is kind of how the template will be with all wells installed, and the center line here is the center line is typically methanol, and it would be hydraulic controls, electrical controls, all of these things, whereas this would be, as said, the production part of it. We'll jump a little bit towards what is more relevant for casing design.
The ROV installed.
Let me see. This is the roof, which is often there just to protect against, say, fishing nets and whatever is coming on top.
FMC's UWD-15 wellhead system.
And here is the wellheads and casings more in detail.
Full metal sealing subsea drilling system. The drill pipe and drill bit are lowered into the hogs and through the bit guide. The pilot hole for the 30-inch conductor casing is drilled using an under-reamer and hole opener. During this drilling operation, a cuttings transport system is also utilized, which is not shown on this presentation.
Yeah, she's talking about cuttings transport system, CTS. What that is, it's like an underwater vacuum. Because when you're drilling, there's a lot of cuttings coming out like a cloud here, and what you can see is like opening your eyes into a drum of mud. It's absolutely nothing that is visible. Very good, honey. What we do is to put up the cuttings transport system in some cases. They may help a little bit, and sometimes it's actually more help. It's more help and assistance in the current. The local current takes away everything, and what you can see even with the cuttings transport system is often just the radar of the ROV, any gas that comes in return. That would be what you're looking at, and on drill floor you're just relying on the depth of your drill string. You know that you have entered the hole, and you're drilling.
Upon completion of the 36-inch hole, the permanent guide base, or PGB, and 30-inch wellhead
og så må dere være stille. Nå holder jeg på med møtet mitt en gang litt til. Må dere være stille.
landed on the hinge over guide or hog. The guide base provides for alignment of the assembly. The 30-inch casing is cemented in place by pumping down the drill pipe and up and around the outside of the 30-inch casing. The 30-inch casing is supported by the drill pipe from the drilling rig, and the cement is then allowed to cure for an established period of time. The 30-inch cam actuated running tool is released by rotating the drill pipe to the right approximately 3 1/2 turns. The running tool is removed by picking straight up with the drill pipe. The hole for the intermediate casing is drilled through the 30-inch conductor pipe to a pre-established depth. The cuttings transport system is utilized in this operation. The 18 3/4-inch subsea wellhead assembly is connected to the last joint of casing. An 18 3/4-inch cam actuated running tool is installed in the wellhead. The casing is lowered and landed in the 30-inch wellhead assembly. The intermediate casing is cemented in place. Cement is pumped down the drill pipe and up and around the casing to ensure a pressure barrier between the strings of pipe. The cement is allowed to cure. The 18 3/4-inch wellhead running tool is released by rotating the drill pipe to the right approximately 3 1/2 turns. The running tool is removed by picking straight up with the drill pipe.
Yeah, what you see here is that the bore protector is already installed, protecting.
The next operation is to test the integrity of the BOP stack and the VX seal. With the bore protector installed, the 18 3/4 inch wellhead running tool is run and landed on the nominal bore protector. The drill pipe is rotated to engage the dogs in the wellhead profile. A pressure test of the BOP stack and VX seal is performed at this time to ensure the integrity of the BOP stack connection. This is accomplished by pumping pressure down the choke or kill lines against the running tool and the closed ram or annular preventer. The testing tool is released by rotating the drill string to the right 3.5 turns. The tool is removed by picking straight up with the drill pipe.
Yeah, this is how the wellhead looks like. And here are the locking profiles that we're talking about. You'll see the wellhead and how. Yeah, we'll look more into it on the inside here, I think.
The drill bit is then lowered and drilling for the 13 3/8 inch casing is performed to a pre-established depth. The drill bit is retrieved to surface. During the drilling phase of the Terra Nova project, optional casing strings of 11 3/4 inch or 10 3/4 inch may be installed. Specific details of the casing programs are located in the drawing viewer of this section. The 18 3/4 inch wellhead tool is run into the wellhead with its retrieval ring expanded. It is landed in the nominal bore protector. The 18 3/4 inch wellhead running tool is then picked up until an overpull is noted. This ensures that the retrieval ring has engaged the profile in the nominal bore protector. Approximately 30,000 to 40,000 pounds of overpull is required to shear the lip seal on the bore protector. The bore protector is retrieved by picking straight up with the drill pipe. The 13 3/8 inch, 10 3/4 inch, or 11 3/4 inch casing hanger assembly is attached to the last string of casing. The 18 3/4 inch single trip casing hanger running tool, complete with seal assembly, is then installed on the casing hanger. The entire assembly is lowered and landed into the 18 3/4 inch high pressure wellhead. The casing is cemented in place by pumping down the drill pipe and up and around the casing hanger. The cement is then allowed to cure. The single trip tool is released by rotating the drill pipe to the right 4 turns. After completion of the 4th turn, the tool will drop approximately 8 inches and will land the seal assembly on the casing hanger. The seal assembly is the primary component providing sealing integrity to the annulus of the casing hanger and wellhead. The seal assembly is weight set with 15,000 pounds of force. The pins in the seal assembly shear, allowing the seal's energizing mandrel to move down, expanding the seal and forming a low-pressure seal. The seal assembly is locked into position by closing the BOP and pressurizing the seal to 3,500 psi for the 13 3/8 inch size, or to 4,500 psi for smaller casing sizes. The pressure forces the lock rings down over the casing hanger and locks the seal assembly to the wellhead if the lock ring has been run. The primary sealing element of the assembly is the straight bore metal seal, or SBMS. These are high-pressure metal seal bump profiles which seal against pre-designed metal seal areas on the casing hanger and wellhead. Metal-to-metal seal assembly used on all casing hangers is the same in all casing sizes. The seal assembly and BOP are tested by applying pressure on the choke or kill line against the seal assembly and a closed preventer in the BOP stack. The single trip tool is retrieved by a straight upward pull of the drill string. The tool was released during the rotation and setting of the seal assembly. In preparation for the next drilling procedure, a wear bushing is made up to the spring-loaded tool. It is run and landed in the high-pressure wellhead. The spring-loaded tool closes with 3,000 to 5,000 pounds of downward weight. If the BOP stack requires further testing, it may be tested at any time with the wear bushings in place by use of the spring-loaded tool. The spring-loaded tool is removed by picking straight up with the drill pipe. An overpull is required to shear the brass shear pins on the running tool and disengage the spring-loaded tool from the wear bushing. This will require approximately 12,000 to 18,000 pounds of overpull, depending on the number of shear pins installed when running the bore protector. With the wear bushing in place, a hole is drilled for the next string of casing. In this case, 9 5/8 inch casing is used. Additional casing sizes may be run. Upon completion of drilling operations, the wear bushing is removed using the 18 3/4 inch spring-loaded tool. It is run down the riser and landed on the wear bushing. Proper space out is noted and confirmed. The wear bushing and tool are retrieved by picking straight up with the drill pipe. It will take approximately 25,000 to 30,000 pounds of overpull to shear the lip seal on the wear bushing.
All right, this is a repetition from here on. All the casings are basically the same. They will have either a bore protector or wear bushing while drilling on top of the previous casing hanger. You drill the section, you retrieve the wear bushing. Typically, what she didn't say is that you actually have to clean a little bit. And then you run casing, and the casing hanger lands on top of the previous casing hanger, and you're setting the seal assembly in the same way as what you did. And let's see if there are any interesting pictures here. Yeah, it's the same basically. What could be interesting to quickly look at maybe would be the connectors. Let me see. Horizontal Christmas tree. The latch connector. Let me see. The latch connector could be. There it is, the latch connector. Here is where you see how the tree connects to the manifold and why we have to do the 1 degree inclination.
The last step of the installation sequence of the horizontal tree is to remove the 18 3/4 inch.
Basically, they probably that was skipped.
The connectors.
Yeah, here it is. You see the connector.
Via the eye walks.
How it is run, it's a hydraulic function that you do, and then it kind of grabs around, and it has to be, yeah, it's a low tolerance thing. All right, guys, I think that's about it. We will stop this presentation now. Any questions as we round off this session? Guys, I can't hear or see anybody having any comments.
Everything is okay.
Everything is clear. Thank you. All right, see you guys on Monday. Thank you. Have a nice weekend when the time comes.
Bye.